In this video, we're going to be talking about the acidity of alcohols. So alcohols are weakly acidic, but this is more relative to hydrogen halides, which are very, very acidic. Alcohols are more acidic, however, than amines and alkanes. So you can see here that the conjugate base of an alcohol is going to be an alkoxide. The alk is coming from the alkyl group, and then the oxide is going to mean this negatively charged oxygen right here. So now we're going to talk about some reagents that we can use for deprotonating an alcohol. Since alcohols are a little bit on the weaker side of acids, they are harder to deprotonate, so we must use a very strong base. And in this case, we would use something like sodium hydride, and sodium hydride will dissociate in solution, giving a sodium ion and a hydride ion. And this hydride ion right here is what is going to deprotonate the alcohol, leaving behind the alkoxide, the sodium ion, and then that is going to combine with the hydrogen that it deprotonated from the oxygen, and it is going to make molecular hydrogen, which will disappear as a gas. You can also use lithium, sodium, or potassium metals, but not as ions. So now we're going to talk about phenols. A phenol is a common name for a hydroxybenzene. So you can see here that the main group on this is going to be the benzene, and that's why the hydroxyl group here is going to be a hydroxy substituent. Phenols are resonance stabilized, therefore they are more acidic than a non-resonance stabilized alcohol. So what this means is that if you have a phenol, you can use a milder base to deprotonate it, and you can use something more common like sodium hydroxide. So now we're going to do a little bit of review. If you don't already know how to use the REO acronym correctly, I highly recommend that you go back and watch the videos on how to determine acidity of a proton quantitatively and qualitatively. And those go into a ton of detail on how to use this acronym. And so that's why in this video, we're really not going to go into a ton of detail on it, but we are going to talk about it a little bit. So remember that A is for atom. What atom is the negative charge on? And remember, when we're looking at this, we're looking at the conjugate base. And that is how we are going to determine how acidic the acid is. So when we're looking at the conjugate base, if the negative charge is on a very electronegative atom, that means that the conjugate base is going to be more stable, and therefore the acid is more acidic. If the conjugate base, the negative charge or that lone pair on it, is resonance stabilized, that also means it is going to be more stable, and therefore the proton is going to be more acidic in that case, and this is what we saw with the phenol we just talked about. And then you have induction. If you have atoms on there that provide you with induction, then that negative charge is going to again be more stable, and that means the proton is going to be more acidic. And then we're going to talk about the orbital. So depending on what orbital the lone pair is on, and how close it is to that lone pair, that is going to mean it is more or less stable depending on what that orbital is.
I hope you found this video to be really helpful. The concepts and information presented in these videos will be true no matter what Organic Chemistry 1 class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you are a currently enrolled Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need about these services on our website, www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online, or just drop in during any of our open business hours. For more information about our current services, please visit our website. Thank you.